Well, my role here today is really to introduce a great example of what we're talking about, and I think we're all going to be inspired by the experience of today's keynote speaker. Dr. Charles Camarda is currently the Senior Advisor for Innovation in the Office of the Chief Engineer at NASA. He began his distinguished NASA career in 1974 as a research scientist at Langley Research Center in Hampton, Virginia. And he did that after graduating from what was then the Polytechnic Institute of Brooklyn, which is now the Polytechnic Institute of NYU because of a recent merger. He received a doctorate in aerospace engineering from Virginia Tech in 1990, but his most important degree, as I'm sure you'll all agree, is the Master's of Science in Engineering he received from the George Washington University in 1980. Now, during his many years at NASA, Dr. Camarda has overseen a number of important research initiatives, including a project that demonstrated the feasibility of a design for drawing heat away from the space shuttle's leading edges during reentry. He had a very personal stake in that issue because, in addition to his role as a top NASA engineer, Dr. Camarda is himself an astronaut. He was also responsible for the development of a hypersonic vehicle capable of achieving orbit from a horizontal takeoff, and in 2005, he was a mission specialist aboard the Space Shuttle Discovery on the return to flight mission. So this was a mission following a very tragic accident that you'll all recall. I'll say a little more in a minute. And among other tasks, the crew tested new procedures for flight safety. In the course of that two-week mission, Dr. Camarda traveled a mere 5.8 million miles and logged 333 hours in space, and once again, saving the most important detail for last, he carried with him a GW flag, which we now proudly display in Alumni House. Now, Dr. Camarda may be best known for his work in evaluating the cause of the Space Shuttle Columbia's tragic loss in February 2003. I'm pleased to note that Dr. Camarda is not only a GW alumnus, but also a SEAS Hall of Fame inductee and a recipient of the President's Medal. Ladies and gentlemen, please join me in welcoming Charles Camarda.
Thank you, President Knapp. Just looking out at the projects that I see today, I'm like blown away. I just have to tell you, and I mentioned this to Dean Darling, I'm amazed at what you guys are able to do. Actually, I'm not amazed because I had the pleasure to dabble a little bit in education and even earlier education. I got inspired and have a passion for innovation. It started about 7 or 8 years ago. And it happened when I was flying across the Atlantic, training for ISS and flying to Russia, reading lots of books about creativity and innovation. And one of the things I realized was that a lot of what these folks were saying in these books and articles, I actually did. I was mentored by people in a research and development institution, NASA Langley Research Center, that was just phenomenal and created a culture and an environment where innovation could happen. And that's one of the things I'm going to talk about. There are lots of things I could talk about in different aspects of innovation that I could touch on, but it would probably take a semester. And so what I'd like to do is talk about the environment. How do you create the environment that makes the magic happen? It's not just putting a bunch of really smart people together in a room. And my ideas and my thoughts in this happened while I was training in Russia, and then something tragic happened, Columbia accident. And it changed my life in a lot of different ways, some of them negative because I was very angry, but some of them very positive. And I'm going to talk a little bit about what it takes to create an innovative environment where the magic can happen. Okay, and this is a quote from a great book by Warren Bennis, Organizing Genius. He talks about these great organizations, these teams, and how did the magic happen in places like the Skunk Works, the Disney Troupe. And one can sing or dance, or one can create an environment where singers and dancers can flourish. You have people that are going to be down and in, experts in their domain, and there'll be other people that will be leading a team, putting the right people together. One of the key ingredients is psychological safety. When you're building a team, is that people have to be able to communicate freely, to dissent openly, to disagree, and you have to encourage people to do that. Eliminate barriers for communication and effective communication, and allow for collaboration. Psychological safety, being able to fail and actually encouraged to fail, because failure is how we learn, but there are ways to learn by failure and make it very effective. Basically, permission to fail was the culture I was raised in at NASA Langley. Okay, we learned by doing things, by trying things, and by failing. But we weren't supposed to continue to keep failing. We had to learn from our failures. The other thing that was great about Langley was people didn't have a hierarchical structure. People deferred to the person with the most knowledge and listened to that person, not the title of that person. You want your environment to be stimulus-rich, a lot of hands-on hardware, sight sounds, models, anything that you could do. It has to be relaxing, it has to be aesthetically pleasing, all those great things that you see at Google, but you also have to allow for the interactions between people from different disciplines. And how do you make that happen? There's a great book called Imagination First by Eric Liu and Scott Nope Brandon. And he describes and defines imagination as the capacity to conceive of what is not or what has never been. And he says that imagination should come first, if you think about it, because you have to be able to have that idea, that vision. And creativity is kind of like imagination applied. You're generating ideas, and then you come up with an invention, a product. It has to be new and useful. Innovation is making that imagination, creativity, and invention relevant, okay? Now you have an invention that helps society in general, the masses. So what questions spur imagination? Imagination answers the what-ifs, okay? Imagine a world where. These are the people like Nelson Mandela, who was on an island, imprisoned, in the middle of apartheid, and he envisioned, he dreamed of a multiracial democracy, and eventually made it happen. Now, I'm going to talk about the Columbia tragedy, because I learned so much from that tragedy. I studied it, I worked with people to try to understand it, and when I see this, and when I see what happened, I call this a failure of imagination. When that piece of foam broke away from the external tank and hit the wing, or somewhere under the bottom of the vehicle, you might say that people were asking what-if questions. People were trying to understand what happened. But they weren't able to. They thought they understood the problem, okay? We had very smart people on the ground, but yet the culture in that environment caused these people not to make the right decisions. When they look back at other instances where we lost a piece of foam from that exact area, the CABE first saw about 4 instances. When they went back and looked, it was a total of 12 instances, bipod foam loss, starting as early as STS-107. Almost over 30 years ago, okay? And what's amazing was, when you looked at it, it's over 28 instances where we had a piece of foam coming off from exactly that location, okay? And a matter of fact, one of them occurred 2 flights before STS-107, and it caused enough damage on the SRB skirt that people took notice, but they still continued to fly. And so, when people, and you'll see the cover of Aerospace America today, when they're talking about a recovery, okay, NASA's recovering from Space Shuttle, but what they're talking about, they're collecting information, and they think they understand the technical cause of the failure. I call this a failure of imagination, because not only do we not understand and are able to predict what made that foam come off, the real cause of the problem was the culture. Being raised in an environment where these people could not make the right decisions. We had almost exactly the same thing happen for Challenger, almost the exact same sequence of events, and the CAPE found that this was very disturbing that we allowed this to happen. And matter of fact, in the Cave report, it says, in our view, the NASA organizational culture had as much to do with the accident as the foam. This was the first time in an accident investigation where the culture was at the same level as the technical cause of the problem. And the only way we're going to solve that is to understand why people behave that way, okay? And what you want to be able to do is develop a culture where people can speak freely and you can dissent and you can ask tough questions. Okay, now this was the Columbia Accident Investigation Board designed this experiment, almost a full-scale test with a full-scale piece of foam, almost the size of what happened, what came off of the bipod for STS-107. People on the ground said there's no way it would cause a problem for the wing leading edge. About 545 miles an hour, 1.67 pounds. Foam has the density of about styrofoam. They were amazed. And people jumped up and down like Scott Hubbard and said, wow, we found the smoking gun. That was just scratching the surface of where the problem was. At the same time that they were designing that test, which I call a slow, stupid test because it took way too much money, and initially they were going to have way too little sensors on it to get real information that they could use. And this is what I call intelligent fast failure. Researchers that grew up like I grew up at Langley, this is at Glenn Research Center, worked together with people at NASA Langley, and using a much smaller gun, were able to test smart, fast, small, cheap, and fail early and often. And they learned more with those small, inexpensive tests than that $20 million test that you saw. And from that, they learned from basic principles how the foam behaved, how it failed, how the RCC wing leading edge material behaved, how it failed. They were developing the constitutive properties, the failure theories, and they were rigorously evaluating it, corroborating it with rigorous testing in a stepwise building block fashion until they conducted this test, this analysis. They conducted this analysis before they ran the big test. Initially, they said, there's no way we could analyze this. It's too complicated. We're not going to do it. We're just going to run this big $20 million test, get a couple of data points. These people generated a physics-based model in less than 3 months' time. People said it couldn't be done. A small team of people did it, and you could look at how closely it approximated the real damage. This is where I had my imagination question. Imagine a world idea. Imagine a world where my what-if question. This inspired me to go in a certain direction, and I'm still working on this. Next, I was on a team that helped look at what astronauts would do to repair the wing leading edge, okay? If we had a hole, what would EVA astronauts, spacewalking astronauts, how would they go out there and do that? Well, I created my own psychologically safe environment because I didn't tell anyone. I went to my good friend Don Pettit. We went in his laboratory garage, and we tested things, and we failed fast and furiously. And we tested hundreds of different ideas, mechanical fasteners made out of RCC, concepts for patches, repairing the wing leading edge, and also repairing shuttle tiles, and that's Don Pettit. I love that guy. He's the Zen beginner's mind. He's a genius in a certain area, but he looks at things as a child does, looking at it for the first time in wonder and amazement. That's a great scientist. We were able to do things that people told us would be impossible, and I was able to fly the stuff that we designed and had built and we certified for flight. The drill bits to drill any size, precise hole through the wing leading edge, the shape of the patch. Otherwise, we would not have been able to fly these repair patches on our mission. And we did it in less than a year. That gave me another idea, and we'll talk about it. But you think about it. If you were able to do that in your friend's garage, how would that inspire you? Imagine a world, what, where, what if? Went out and I said, you know what, we could teach this. We could teach creativity and innovation. Everyone is creative and innovative, and you see it right here. We can enhance it. We can exercise that right side of your brain in addition to your left side of your brain so that you could be more creative. And I wanted to pick a challenge to prove that this would work. I always like putting my neck on the chopping block because it's so much more exciting when you have something to lose. And I said, you know what? I want a challenge that even NASA can't solve. And I want to try these ideas for building teams and for solving problems. They gave me carte blanche to let me take some professors from Penn State, MIT, Georgia Tech, and we just wanted to solve a problem that NASA couldn't solve. If any of you, you might know that we land our capsules in the water. Well, the Orion vehicle and the Constellation program, their goal was to land that capsule on land. They were never able to do it. I said, okay, let's take that. That's a good challenge. And so we created the environment. We went to Penn State, and we created an environment. We picked a very nice setting out in the middle of State College, I think it is. There's not much to do out there. And we had, it's not like a big city out there, right? So I had these people. I picked 30 young NASA engineers, and I said, you know what? I'm going to try to train and teach young NASA engineers how to do this. Because what I was amazed was when I saw the accident happen, I saw NASA engineers struggling with ideas and struggling to try to make it happen, which is why I took a handful of people and went outside the fence. We're in State College. We have 30 young NASA engineers. We created an environment that was playful. We taught people that it was okay to fail. We had Jack Mattson from Penn State, who wrote the book, Innovate or Die. We had lots of hardware and material, and we had lectures by experts. A lot of people likened it to a boot camp. I had these people sequestered, these poor people, and we worked day and night. And it was almost like midweek they were going to revolt on me. You know, they were so upset. And, but they didn't. And amazing things happened. And they came up with lots of different ideas. And one of the things that happened that I was really really encouraged to see was that a NASA manager said, you know what, I like this idea. I think I'm going to fund this, okay? I got to walk over here, huh, so that you can hear me. What we did was NASA funded Penn State and Georgia Tech, and it was an experiment. We wanted two universities to work together, okay? Took one of those ideas, and amazing, and this is, so when we were at Penn State, we also utilized the Penn State Learning Factory. And that's another aspect of the creative environment. You want a place to rapid prototype, test ideas quickly, okay? And it was wonderful. These guys jumped in there. They were building things. We were actually testing some of their ideas in a week. And so we went to Penn State and MIT. They took an idea called a personal airbag, which was inspired by a biologically inspired design idea, by how seeds protect their embryos. We had Jeanette Yen was one of our faculty, and so she lectured us on biologically inspired design. We did some research in it, and one of those, actually, those ideas evolved into what looks like this airbag/seat. And if you look at it, what was amazing was kids from MIT and Penn State tested it, 48 tests. We borrowed a crash test dummy from 5 minutes. 5 minutes, I'm almost there. Crash test dummy from NASA Langley. What was amazing was they proved that this idea would work. And not only would it work, it could save 265 pounds in mass, which, if anyone working on the Constellation program, that was a big deal, but it increased the habitable volume by being able to be collapsed. It was amazing. And so this inspired me to have another idea. And so what I want you to do is think about what those ideas could be. Imagine a world where, and these are some of the things I'm working on right now, and I'm working with MIT, Penn State, Georgia Tech, hopefully NYU, hopefully GWU. The first idea I had was, imagine an environment where we solve problems differently. You guys are digital natives. There's no reason why we should be going to meetings. We should be able to hook up in an open environment, crowdsource, take an epic challenge, bring it to the masses, and come up with a solution. There's no way that we couldn't come up with an analytical prediction of what that phone would have done when that crew was in orbit. We should be able to do that, okay? And that's one of the things I'm working on. The other thing I'm working on is, why don't we take these epic challenges that NASA has, DOD has, industry has, and take them out to the universities and farm them out to the masses of students around the world. Epic challenge, real challenges. You don't have to be gaming to escape reality and have this rush. Kids around the world could be working on real challenges, and from middle school on up, I guarantee you, we would have, and NASA would see, creative ideas that no one ever thought of. I have no doubt, if I had a handful of high school students in Don Pettit's garage with me, we would have had tens more ideas. Imagine now we take that to the nth degree around the world. NASA would be able to look at hundreds of ideas simultaneously and have them matured for very little money before they make the selection. Increase the intelligent selection in the concept design phase. The last idea was really what I'm doing with education. We have so many kids. I could ask you, how many people out there, when someone tells you you can't do something, what do you do? What do you do? If you're like me, you are motivated like 10 tigers to try to prove that person wrong, right? And you're also motivated by solving problems. And there are lots of problems out there. There are lots of epic challenges out there. Just in aerospace, you could pick epic challenges in every enterprise, every discipline, and we're creating courses for kids from undergraduate down to middle school wrapped around these epic challenges. Imagine if you're a kid in middle school and you say, gee, I want to be a fireman, or gee, I want to be a civil engineer. Where's a great challenge? You could pique that kid's interest. You could develop the online tools that these kids could go to and learn on their own with just a little bit of facilitation, a little bit of guidance. And so that's it. If you have any ideas, you can reach me right there. If you want to be a part of any of these challenges, I'm trying to convince NASA that this is something we could do. I'm not asking NASA for a lot of money because I don't want them to tell me how to do it. I want to go out there and make it. I want to go out there and make it work. Thank you very much.